We now discuss a localized version of the positive mass theorem. More precisely, we start with the positive mass conjecture with arbitrary end. So suppose that M is an arbitrary complete Riemannian manifold of dimension at least 3, which has non-negative scalar curvature. Moreover, suppose that E is a single asymptotically Euclidean end in M. Then the conjecture is that the ADM mass of the end E must be non-negative as well. Let me comment a little bit on this conjecture. So first of all, it goes back to the work of Shen and Yao in the 80s about conformally flat manifolds, where it is shown that it implies a certain Liouville conjecture for locally conformally flat manifolds of non-negative scalar curvature. In a recent preprint, Lesueur, Unger, and Yao proved this conjecture up to dimension 7, assuming that the chosen and E is asymptotically Schwarzschild. So I will not give the formal definition of an asymptotically Schwarzschild metric. However, it has an asymptotic that is better than just asymptotically flat. Now, in the spin setting, this conjecture has been addressed by Bartnik and Crucial using Wheelen's method. And moreover, they also proved a related rigidity statement for the case of zero mass. That is, they prove that if the ADM mass of the single asymptotically Euclidean end is 0, then the manifold is flat, and hence it must be isometric to the Euclidean space. We now review the approach of Lesueur, Unger, and Yao on the positive mass conjecture with arbitrary ends. They deduce this conjecture from the following theorem, which is of independent interest. So suppose that M is a asymptotically Schwarzschild manifold that is not assumed to be complete or have non-negative scalar curvature everywhere. Moreover, let U1 and U2 be nebulous of infinity with U2 with a closure of U2 contained in U1. Moreover, suppose that there exists a constant D greater than 0, such that the following three conditions are satisfied. So first, G has no points of incompleteness in the D neighborhood of U1. The second condition is that the scalar curvature is non-negative in the D neighborhood of U1. And finally, the third condition is that the scalar curvature satisfies the following inequality on the closure of U1 minus U2. So this inequality said that skull G in this set is greater or equal than, well, than a quantity that depends on D and on the distance between U2 and the boundary of U1. And moreover, this quantity on the right-hand side goes to 0 as D becomes larger and larger. Well, if these conditions are satisfied, then the ADM mass must be non-negative as well. Here, I drew a picture to illustrate the situation. So first of all, we consider the case of a single asymptotically Euclidean end, asymptotically Schwarzschild. Well, this green region is the neighborhood U2, and then this is the neighborhood U1, and finally here you have the D neighborhood of U1. So in other words, the green region is U2, the red region is U1 minus U2, and the blue region is the D neighborhood minus U1. And the red region is exactly the region where the scalar curvature satisfies this inequality. And the other assumptions is that the scalar curvature is non-negative on the green region and on the blue region. Outside of the of the D neighborhood, there are no assumptions at all. Now let me quickly explain the reason why the previous theorem implies the positive mass conjecture with arbitrary ends. Well, this depends on the following property of asymptotically Schwarzschild matrix. So suppose that M is an asymptotically Schwarzschild manifold with negative mass and non-negative scalar curvature. Then there exists a conformal factor phi such that the conformal metric G tilde is asymptotically Schwarzschild. Moreover, it has scalar curvature strictly greater than 0 in a neighborhood of infinity. And finally, phi is constant outside of a certain neighborhood of infinity. So which means that, in other words, we can assume that the scalar curvature is strictly positive in a neighborhood of infinity. Now, if you assume that the manifold is complete, then we can take the D neighborhood larger and larger. So we can take D larger and larger, and therefore this inequality. So let me go back on until this inequality on the red region is satisfied, and therefore, of course, you would get a contradiction. So in this way, Professor Ungari-Yao proved the positive mass conjecture for arbitrary ends. So take M be an arbitrary complete Riemannian manifold of dimension at most 7, which has non-negative scalar curvature. Moreover, suppose that E is a single asymptotically Schwarzschild end in M, then the ADM mass must be non-negative as well. And this, as I already said, addresses the positive mass conjecture with arbitrary ends when the dimension of M is at most 7 and the end E is asymptotically Schwarzschild. In their proof, they use mu bubbles. So this is a localization technique for the minimal upper surface method, which is due to Gromov and which has been recently used to solve other interesting questions. Now I want to point out the relationship of the positive mass theorem with the Garrosh conjecture. Now, in the complete case, the positive mass theorem is actually a consequence of the following theorem. So suppose that Y is a closed n-dimensional manifold, then the connected sum of Y with the torus does not carry any metric of positive scalar curvature. So this theorem up to dimension 7 was proved by Yao, and this has been recently extended to every dimension again by Yao. In the spin case, this follows from the work of Gromov and Lawson on a largeable manifold. Now the relationship between this theorem and the positive mass theorem is given by the following theorem of Locamp, which is, well, suppose that there exists a counterexample to the positive mass theorem, and then there exists a metric of positive scalar curvature on the connected sum of the torus with the compact manifold, which is obtained by taking one point compactifications of all the asymptotically Euclidean ends. So in other words, any counterexample to the positive mass theorem would also give a counterexample to the Garrosh conjecture for connected sums. Now it's natural to ask what happens in the non-compact case. Now consider the following setup. So suppose that X is an open n-dimensional manifold. And now the connected sum with the torus is again an open manifold, and therefore it always carries a incomplete metric of positive scalar curvature. This is due to a classical result of Gromov. And therefore, what we can ask is whether the connected sum carries a metric of positive scalar curvature satisfying some extra geometric conditions. Of course, a natural condition is to ask for completeness, and this has been addressed recently by Chodosh and Lee. So they proved that up to dimension 7. So again, they use the minimal upper surface technique. Take any n manifold X, possibly open, then the connected sum does not admit any complete metric of positive scalar curvature. So they actually also proved a rigidity statement that I will not discuss in this talk. Again, notice that in the proof of this theorem, Chodosh and Lee used rebubbles, so the localization for minimal upper surfaces. So one can ask whether this theorem implies the positive mass conjecture with arbitrary ends, but as pointed out by Lesourd, Unger, and Yao, it is not clear whether a compactification argument a la Lecamp is available in this case. So more in general, it makes sense to ask whether the metric inequality of Lesourd, Unger, and Yao holds for the connected sum of the torus with an open manifold X. Let us now see what is known in the spin setting. So suppose that X is an open n-dimensional spin manifold. Then the connected sum of X with the n torus does not admit any metric G, satisfying one of the following conditions. So first, G complete and of positive scalar curvature. So this follows from the work of Gromov and Lawson on enlargeable manifold. This condition can be slightly strengthened by requiring that G is complete, the scalar curvature is non-negative everywhere, and is positive in a neighborhood of the torus minus a disk. Of course, I'm identifying the torus minus a disk with a subset of the connected sum. This result is due to myself. Finally, there is a third class of metrics that can be ruled out. So in particular, if there exists codimension 0, some manifolds with boundary omega-1 and omega-2, such that these inclusions are satisfied, and moreover, there exists constant kappa greater than 0 and L between 0 and pi over n square root of kappa, such that the scalar curvature is non-negative in omega-1 and is bounded from below by kappa n times n minus 1 in omega-2 minus omega-1. And finally, the mean curvature of the boundary of omega-2 is greater or equal than minus the square root of kappa times the tangent of n, of this expression, and the distance between the boundary of omega-1 and the boundary of omega-2 is greater than L. Here I drew a picture to explain the situation. So this is the manifold omega-1 and the manifold omega-2. Now we require that the scalar curvature is non-negative in this region, and in the red region, which is omega-2 minus omega-1, we require the scalar curvature to have a certain positive lower bound, plus we have conditions on the mean curvature on the boundary of omega-2 and a condition on the distance between the boundary of omega-1 and the boundary of omega-2. And note that we have no conditions at all outside of omega-2. So in this sense, there is an analogy with the theorem of Lesourd, Unger, and Yao. Notice that without any information on the mean curvature of the boundary of omega-2, we obtain the upper bound, the following upper bound. So there are no metrics on the torus connected with X such that the scalar curvature is greater or equal than 0 on omega-1. And again, we keep the same lower bound in omega-2 and omega-1, and the distance between the two, between the boundary of omega-1 and the boundary of omega-2 is greater than this constant. So in other words, we get an absolute upper bound. Now, parts 2 and 3 of the previous theorem are proved using Calias operators. So Calias operators are a localization method for Dirac operators, which is obtained by adding a potential to the Dirac operator. And this method has analogies with Gromov mu bubbles. We now state the main question that I want to discuss in this talk in the spin 7. So consider the following situation. So let X be a complete asymptotically Euclidean Riemannian manifold with compact boundary. Now suppose that X0 and X1 are codimension 0 submanifolds, well, such that these inclusions are satisfied, and such that X0 contains all asymptotically Euclidean ends of X. Moreover, suppose that the scalar curvature is greater or equal than 0 on X and is greater or equal than a certain constant, than a certain positive constant on X1 minus X0. Then the question is whether the Dirac localization techniques can be used to relate the distance between the boundary of X1 and the boundary of X to the ADM mass of the manifold X. So in other words, we are asking whether you can use localization techniques to get an inequality which is similar to the one of Lesueur-Ungary-Yau. This is the picture. So notice that it's different from the previous one, because in the previous one we were using information only on this part of the manifold. Now we want to use information on the lower bound of the scalar curvature on this region and the distance to the boundary. Now, if we can answer this question, then we would expect similar results to hold also in the case of the Garrosh conjecture